right.
Stay here.
So first of all, let me thank the Opta team for having us here today. It's a great pleasure to be there. And also, who are we? Like as Ryan said, we have a quantitative finance background. So Otman is a PhD student in quantitative finance. I'm a professor of quantitative finance. And actually, most of my students, they are working here in London, but in the bank industry. So let me explain how it works in quantitative finance, because basically we're going to proceed the same way for football modeling. So what do we do in quantitative finance? Well, our first step is to use data science on past data. So let's imagine that I'm interested in the stock like Google, Apple, Boeing, and BNP Paribas. The first step of my analysis is to take past data to understand the dynamic of this stock. So I want to analyze my data to understand in the past, say, what's the risk of BNP Paribas, what's the trend of Google, and so on, what is the correlation between my assets. This is the first step, analyzing past data through data science tool. Once I know how my data are looking like, I can try to do simulation. And then I'm going to use probabilistic tool and artificial intelligence. Why do I want to do simulation? Because I want to forecast the future evolution of my asset and, in fact, the future evolution of my investments. I want to know how Google is going to be in the future. I want to know how BNP Paribas is going to be in the future. In fact, I want to know how my portfolio is going to behave in the future. Is it going to be risky? Is it going to be non-risky? Am I going to make money out of that or not? I want to be able to test for that, and so I need to get some simulation device. And then, once I get this simulation device, I can try to optimize. So let's imagine that I have a given amount of money, and okay, how do I want to invest on the market? How do I split this money between Google, Apple, Boeing, and BNP Paribas? Okay, what's the optimal way to split my money? And what do I do if, at a given amount of time, well, I'm no longer happy with my portfolio? How do I change my portfolio? What are the optimal times to change my portfolio? This is what you typically do in finance, and how you can quantify if you made the right decision or not. Well, so as you can see, we're going to use some quite sophisticated mathematical tools, but what we should not forget is that we are just trying to help the manager to make his decision. We are not replacing a very experienced asset manager, which is going to have a very deep feeling about the market. We just want to help him. So we're going to adopt the exact same paradigm in football modeling. Okay, so how is it going to work? Well, I'm going to replace the assets by the players, the markets by the game. My portfolio strategy is going to be the player I'm going to select, the tactic of the coach, the substitution. What do I want to optimize? No longer my profit and loss, but the score. And who is going to be the asset manager? It's going to be the coach.
Thank you, Mathieu. So now I'm going to show you the relevant indicators or analytics that we are going to use to feed our model. So all this analytics are based on the F24 data feed. So to compute our analytics, we are going to consider the following decomposition of the field. So this is not the optimal decomposition. It's not fixed. It can be refined, but for our goals, it is enough. So we are going to consider the following decomposition in 18 zones. So the first indicator is the player location. So we want to take into account how players move in the field. So for instance here, so this is a simple indicator. It is the empirical distribution of Benjamin Mendy, which is a left defender on the field. And we can see, so the graph shows that most of the time he's on the left side of the field. So the second type of indicator is the interception. So players' ability to intercept the ball or their capacity to take the ball from the opponents. So here we plot just, so it is easily done, it can be easily done. We plot the total number of interception for one given player. So this type of information, we give it also to our algorithm. So we have also other types, more sophisticated indicators that takes into account how the player interacts with the other zones, how the player receives the ball from a teammate, and we also add expected goals, and we have a new and personalized indicator which enable us to compute how one player participates or is involved in the global team effort. So, and this indicator, so the last one, we need tracking data to do it. And so not everyone has access to tracking data, so how are we going to do? So the idea here is to create our own tracking data based on the F24 database. So the idea of how to create our tracking is the following. We are going to consider three components. So the first component is the linear components. So basically the main idea here is that we force the player to be at the right place at the right moment to get the ball. So we force the player to be at the right place to receive the ball, and he moves linearly from its old location to the ball location to get it. So the good point here is that we are sure that the player is at the right location. The bad point is it leads to unrealistic movements, because a player who does not reach the ball or touch the ball many times will never move with only this component. So we add a second component, which is called the quantile components. So the basic idea here is that we start from the graph on the left side. So this is for a given composition, so 4-4-2, the average position of players in League One under the 4-4-2 strategy. So, and each time where the player with the ball, so, and on the right-hand side, we have the empirical distribution of left-back defender. So each time when the player with the ball deviates from its average location with a certain level, so this level is going to be called quantile, the other players are also going to deviate with the same level, with the same quantile. So the good point here is that the players are going to follow the ball movements, and they are going to follow the player with the ball movements. We have dynamic moves. However, very extreme movement of the player with the ball may lead to very extreme movement of all the other players, And this is the drawback, the main drawback of this component. We add finally a Voronoi component, so we have already seen this similar graphs. So basically the idea behind Voronoi cells is that each player has one cell, and this cell represents its influence area. So the idea behind this component is that the team with the ball, the attacking team, is going to try to maximize the overall, its global influence area. So players of the team with the ball are going to move to maximize their influence area, and players without the ball are going to move to reduce the influence area of the opponents. So we can make the model more sophisticated by adding weights to the most dangerous zone. So the most dangerous zone, we add weights to them. And it leads to more realistic ball movements. And typically, it leads to 1-1 duel. For instance, here, the graph on the left, so this one, we can see that each defender tries to stick to the attackers to reduce the area. The influence area of the opponents. And the final simulator is indeed just a suitable combination of these three components. So let's show how it looks like. So this is a sample of tracking. This is an example. So we took the Real against Barca match. So on the right side, we have the real match, so here, and on the left one, we have the replayed match. So there is a small delay on purpose, and now we can see that Kroos is going to take the ball on the real match. He's going to take it with some delay. He's going to give the ball to Marcelo. Marcelo moves forward. He passes it to Cristiano right here, and we can see that they are similar. The composition of the teams are almost similar, and then we have the ball to the touch. So no.
All right, so now that we have emphasized a lot of relevant analytics, we can use that to build our simulator exactly as what we would do in finance. So now the goal is the following. I want to be able to simulate a game between two teams, right? Why do I want to do that? Because as a coach, I want to forecast relevant quantities. I want to forecast the score. I want to forecast the possession. I want to forecast the name of the strikers. Of course, all that with confidence interval. And this will help me to optimize my coach strategy. Note that the simulator that we're going to present is you don't need the player to play together to use the simulator. You can take players coming from different horizons, put them in a simulator, and see what it's giving. So we use that, for example, for national teams. So in the following, I'm going to use the same 18 zones as the ones presented by Osman. So how does it work? Okay, so imagine that I have the player I1 is in the zone J1. So what's going to be the next action? So maybe my player I1 can give the ball to a teammate in the zone J2, okay? Or maybe my player I1 can lose the ball to a guy from the opposing team in the zone J2, or maybe my player I1 can just score, right? This is essentially what can happen the whole sequence of possible action. And the thing is that in our modeling, the probability of these events are going to depend on the state of the game, which means that it's going to depend on the players, it's going to depend on their ability, it's going to depend on the opposing team, it's going to depend on the score, it's going to depend on the tactic coach, and it's going to depend on the time remaining until the end of the game. So particularly important is the ability of my player I1 to do a pass to J2. Particularly important is the ability to the guy from my team in J2 to receive the ball. And particularly important is the ability from the guy from the other team in J2 to intercept the ball. So we use artificial intelligence and machine learning to calibrate this algorithm. We feed with a huge number of analytics, and there is automatic selection of the relevant variables, and this model is calibrated on this Opta24 data. Right. So now, okay, I'm telling you a story, I have a good simulator, so how can you trust me that the simulator works in practice? So what can I do? I can just do simulation, compute statistics in my simulation, and compare the statistics that I get in my simulation with what I get on real data, right? So the first thing that I can do is look at this transition matrix. So what is that? This is on true data. It's, okay, when the ball is in zone 8, what are the likelihood that the next action, the ball is going to be here in zone 1, here in zone 2, here in zone 3, here in zone 4, and so on. Okay, so this is the likelihood that you get on data. This is the likelihood that you get when you simulate one given match, like it was Paris Saint-Germain against Lyon in our simulator. So you see that at the visual level, the transitions from one zone to the others are very close. Okay, so this is a good point. And we can also look at individual characteristics. So for example, here is when Edinson Cavani is in zone 14, which is here, where is the ball going to be the next action? Okay, so when Edinson Cavani is here, very often the next action, the ball is still here, but sometimes it's here, sometimes it's here, sometimes it's there. Right? This is what you get on the data. This is what you get from the simulator. Again, it matches pretty well. Right? And to finally convince you, we did the following exercise. What we did is we took the first part of the season 2017 and we calibrate our model on the first part of the season 2017, right? So we calibrate the model, and then we play the championship, the second part, completely blindly, okay? And we do that 100 times, okay? Because this is a simulator, so each time I have new results. Okay, so we play the championship 100 times, and so which means that I have 100 rankings at the end of my simulation. And what I'm showing you here is the average ranking you get after the simulation. So what you see is that this ranking is very reasonable. It's quite close to what happened in practice. And remember that in this season, actually, Monaco won the championship. Okay, so it's very accurate here. It's very accurate here. And what is very important to us is that we are able to give standard deviation, right? So I'm not saying I'm sure that Dijon is going to end here. I mean, there's a big standard deviation, which means that I'm not really able to forecast what's going to happen for Dijon. Right. So now that we have a good simulator, we trust the result of our simulator, how can I use that to really, in practice, optimize the decision of the coach? So imagine that I'm before a game. I know that tomorrow I'm going to play against a given team. I'm the coach. What are my possible actions before a game? My possible actions are the choice of my players and the choice of my tactic, right? These are my possible actions before the game. And what we are going to be able to do is to optimize these choices. Indeed, we have a simulator, but the dynamic of the simulator, of course, will depend on my choices, right? So my simulator is not going to behave the same if I choose this composition or if I choose this composition, right? So the behavior of the simulator is going to depend on my choices, and what I want to do is to find the composition which is going to lead to the best possible outcome. And so I have to fix a criterion. Let's say our criterion is the score. What I'm looking for is the best composition to optimize my expected score at the end of the game. Right? Okay, so there is a mathematical theory to do that, which is called stochastic control. So again, I'm before the game. I'm looking for the best composition, the best tactic to optimize my final score. Right. So I can do that before the game, but also I can do that during the game, because as the coach, during the game, I still have some actions which are possible. I can do substitutions, and I can change the composition of my team. Right. So a very important tool to do that is the so-called value function. So what is the value function? This is this function VTUT. So this is the best expected score you can get at the final time capital T, provided that you do the optimal thing between T and capital T, knowing that the state at time T is given by UT. So what is the state? That you are at time T, it's minute, say, 24. Minute 24, you have these players in the first team, this player in the second team. the score is equal to this, there is just a few times remaining. What is the best that you can expect if you act optimally? This is the so-called value function. And this value function, we can monitor it in continuous time. And what we are looking for the action which is going to lead exactly to the value function. Because the action leading to the value function are going to be the action which are leading you to the optimal result. Okay? So if I'm before the game, it's just V0, U0. Okay? So I'm at time 0. U0 is just the tactic that I'm going to choose, the composition that I'm going to choose. And this is my best expected score, knowing that I have chosen this composition and this tactic. Right? And so I can monitor that continuously, I mean, at the beginning of the game and during the whole game. Let me give you some examples. So this is an example of the round of 16 of the last Champions League. So we played the game of monitoring live this value function. So let's first imagine that I'm not allowed to do any substitution. Okay, I'm not allowed to compute any substitution, and we have computed the value function at the minute 76 for the given team at this moment. Okay, this was the value function. This is the best you can expect with this given team at this moment. Then I allow myself for one substitution. Then, and if, for example, so the optimal substitution was to replace Benzema by Bale, and then you see the value function is improved by 4%, right? Which means that this was the optimal decision to take at this moment, and this we can monitor in continuous time. And very importantly, we can quantify all this. It's not just like, I have the feeling that Bale should replace Benzema. Based on our algorithm, and of course it's only the algorithm, there are many other parameters we are not taking into account, we can exactly quantify the interest of replacing Bale by Benzema. Just a graph to show you like mathematically how it works. So here, it's the time during a second half. Okay? It's the time during a second half. And in red, so let's look at the red curve, for example. So this is for a game Paris Saint-Germain against Lyon. We assume that Lyon is not doing anything special. Lyon is keeping the same team. And Paris Saint-Germain is going to act optimally. Okay? Paris Saint-Germain is going to act optimally. So if the score is 0-0 at the beginning of the first half, this is the best score than Paris Saint-Germain can expect. Okay? If the score is 0-0 15 minutes before the end, this is the best expected score that Paris Saint-Germain can expect. And if the score is still 0-0, like 2 minutes before the end, well, it's going to be 0-0 in the end. Okay, so you can really compute that in real time. Same things with the changes. Okay, so let's again look at the red curve. So the red curve is that, okay, you can still do 2 changes. If you can still, so this is minute 45. If you can still do 2 changes, if you act optimally, the best expected score that you can expect is given by this. If I can only do 1 change, it's just this. If you can do 0 change, it's this. And at the end, of course, if you can do still 2 change, 1 change, or 0 change, it doesn't change anything because it's the end of the game, right? So the point is that you can really monitor that in continuous time, and really at any given time moment, you can monitor the optimal decision. So it's not saying that, okay, you should absolutely do what the algorithm is saying, but it's telling you that if it's telling you something, maybe it can be an hint that there is something to look at. Right. So this was during the game, and actually you can, as I said, you can do that before the game, and we used it for the French national team before the World Cup, estimated on data before the World Cup. So what we did is to take some fixed composition for this possible opponent to France, just run the algorithm, and make the algorithm choose the optimal composition of France according to his criterion against all these teams. So what is quite interesting here is that Ducy by himself, the algorithm is choosing different teams depending on the opponents, right? So the algorithm is choosing different teams depending on the opponent. In particular, it's very hard to explain why, but like here against Portugal, the team is really very different, right? I don't know, maybe because there's a very specific player in Portugal, I don't know, but the team was very different. Other interesting point is that if you look at these teams, actually they are quite close to the team chosen by Didier Deschamps at the beginning of the World Cup. Okay, he more or less played like this at the beginning of the World Cup, and then he realized it was maybe not the best idea, and then he changed the composition. But he started more or less with this kind of team, except that Thomas Lemar was not playing too much. It was Dembélé, but quite the same profile. Right? So this is just optimizing value function. Okay, just looking at the action which are leading to the optimal value for the value function. And finally, there is something which is interesting that we can take a game who already took place and try to find if the player, try to assess if the players took the right decision or not. So we can really grade the decisions of the player. So how can we do that? Let me just give you an example. Okay, so this is this is a past game. You just take a snapshot of the game. The situation is like this. Okay, so this is Paris Saint-Germain against Lyon. Paris is in blue. The situation is like this. Thiago Motta is going to receive the ball here. Okay, Thiago Motta is going to receive the ball here. So what I can do is just compute my value function at any possible location. Okay, so remember that I have these 18 zones. So I can compute the value function in the 18 zones, provided Thiago Motta is able to put the ball there, okay, in a successful pass. So if Thiago Motta is able to do a successful pass here, the value function is going to be 1.62. If Thiago Motta is able to put the ball here, the value function is equal to 1.29. Okay, so of course, but this is a bit silly if we just look at that. I'm just saying that if I'm going to get very close to the goal here, the value function becomes higher. So of course, these figures, I need to discount them by the probability that Thiago Motta is indeed able to make the assist, right? So is the assist possible or is the assist not possible? And so this is what you can see on my second graph. So the second graph is giving you this. So for the 18 position of my field, what I'm computing are the likelihood of all the possible events. What are the possible events? For example, here is in yellow, it's positive, which means that you have the pass is successful. In white, it's negative, it means that you have lost the ball. So for example, Thiago Motta is here. There is a probability of 0% that he's going to make a successful pass here, and there is a probability 0.06 that he's going to lose the ball here. Thiago Motta is here. There is a probability like 4.99% that he's going to make a successful assist here. There's a probability 0% that he's going to lose the ball here. Okay, and we do that for all the location. So what you see is that when Thiago Motta has the ball here, what is the most likely case? He's going to keep the ball here. Okay, so maybe he's just going to dribble like this, stay in this area. Okay, 58.66%. The interesting point is to look at this. Okay. If you look at this area, okay, so Thiago Motta, there is a probability 4% is going to try to make this assist here, and it's going to be successful. And with probability, say 0.1% is going to try to make the assist here, and he's going to lose the ball. But the thing is that now, let's think conditional on the fact that Thiago Motta has decided to do that. Okay, conditional on the fact that Thiago Motta has decided to do that. What is the success probability? It's 4% divided by 4% plus 0.09, which is huge, right? Because we can argue on conditional probability. So if he has decided to do that, if say, what is the probability that is successful? Well, the success rate is super high, okay? And we know that the value function here is very high. So this would have been a great move, and it's a possible move, right? We took this configuration on purpose, because you see, there is a line where I can do the pass. We took this configuration on purpose. Whereas here, remember that the value function here is the same as the value function here. But if you look at here, if Thiago Motta is trying to do this pass, the success probability is almost 0. Okay? So we can try to do this pass, but the success probability is almost 0. So it means that based on the value function, based on this success and failure probability, you can definitely compute kind of optimal behavior of your football player for given action in the past. Right? So I told you that what is cool with this algorithm, it's, okay, this is artificial intelligence. It's a bit a very pretentious word, but we have to use it because everybody uses it. It's a very pretentious, but this is artificial intelligence, which means that it's selecting the variable automatically. So we feed him with a lot of variables, and he's feeding the interesting variable to characterize the players automatically. So we took the variables enabling us to characterize the player, and then what we did is exactly as this morning, we tried to do scooting with these variables coming out of our algorithm. So just as an example, we took the case of Thiago Motta in 2016-17, and we tried to replace Thiago Motta. Okay, we are looking for a guy who looks like Thiago Motta in 2016-2017, taking a guy from the year after. Okay, so we take the characteristic of Thiago Motta in 2016-2017, consider all the guys the year after, and try to look somebody who looks like Thiago Motta. Again, we can also do that with a fake player. I can create a fake player with fake characteristics and look if there is a player in one championship looking like him. Just to show you what we get, and again, the interesting point is that this is completely blindly. This is, in order, the players who, according to our algorithm, are looking the most like Thiago Motta. Again, maybe it's not the right idea to look at somebody looking like Thiago Motta, but this is just what we did. And I mean, you're much more specialist than us, but I believe that this list is reasonable, right? So this is the list of the player looking like Thiago Motta in 2017-2018, right? In order. Right, so I'm going to end here, but just before ending, I would like to thank Joe Ferrelli, because he helped us a lot to improve our presentation, and also Mathieu Lacombe, Clément and Adrien from Paris Saint-Germain, who also helped us with great comments. Thank you very much.